Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module I will be talking about how to apply the regular perturbation methods to problems involving differential operator. So we will be using the regular perturbation method on initial value problems. So example 1. So we will directly exhibit our method using an example. So the problem that I have is that of a non-dimensional. We have already seen this differential equation a few modules back. So this is the non-dimensional projectile problem, and this is the differential operator that equation that we had seen for this equation was u tau tau is 1 by 1 plus epsilon u whole square, where u 0 is 0 and u tau 0 is 1, right? And we see that u is can now be, we are again going to use, as usual, we are going to use a power series expansion of the solution. So u is u naught. This time the coefficients of the power series will no longer be constants but will be a function of the independent variable tau. So u naught of tau plus epsilon times u1 of tau and so on, right? So and epsilon square u2 of tau and so on and so forth. Now notice that we could expand the right hand side of this problem using binomial expansion. So 1 by 1 plus epsilon u whole square is 1 minus 2 epsilon u plus 3 epsilon square u square minus and so on and so forth, right? So we see that now if we were to use the expansion of u from this, let us call this problem as 1, the expansion as 2, and we plug this expansion 2 into these factors, we see that this is 1 minus 2 epsilon times u is going to be u naught plus epsilon u1 and so on, and then plus 3 epsilon square u naught plus epsilon u1 and so on so forth square. Okay, so then we have that this is 1 minus 2 epsilon u naught plus 3 epsilon square u naught and so on, right? So now what we have is the differential equation. The differential equation can be written as, now on the left hand side we will have the differential operator. So this is u naught double prime plus epsilon u1 double prime plus epsilon square u2 double prime and so on so forth. This is also equal to, on the right hand side we are going to retain the highest order terms. This is 1 minus 2, well, we had a minus on the right hand side, so we should put a minus, and we have a minus sitting outside, and so we will have minus and so on so forth. So we will have minus 1 plus 2 epsilon u naught, and that is what we have up to the largest order term, right? So now we could start, well, this is the differential equation. What about the initial conditions? So the initial conditions could also be expanded. We see that u naught at 0 plus epsilon u1 at 0 plus epsilon square u2 at 0, this is equal to 0 from the first initial condition, and from the second one we see that u naught prime at 0 plus epsilon u1 prime at 0 and so on so forth, this is equal to 1 from the second initial condition, right? And we see that if u naught of 0 is we can start to equate all the order epsilon terms in the initial condition, and we will see that u naught of 0 is 0, u1 of 0 is 0, and so on and so forth. And on the second initial condition we see that u naught prime is 1 and u1 prime is 0, and so on. All the higher order terms are 0. So let me just write what I just said. So u naught at 0 is u1 at 0, and so on and so forth, u2 at 0. This is all 0, while u naught prime at 0 is 1, because the highest order term on the right hand side is 1, which doesn't have any powers of epsilon multiplied. And then similarly we will have u1 prime at 0 is u2 prime at 0, and so on and so forth. This is equal to 0, right? And then what we have is we can now so this is our initial conditions. So now we can start to solve each orders of the initial condition. So the largest order is epsilon to the power 0. So epsilon to the power 0, left hand side is u naught double prime, right hand side is minus 1. So we solve order epsilon to the power 0 differential equation. We get u naught double prime is minus 1, and the initial condition is u naught of 0 is 0 from here, and u naught prime at 0 is 1 from this condition. So we solve this second order differential equation. We see that this is going to be tau times 1 minus tau by 2. And then similarly, order epsilon to the power 1 term comes out to be u1 double prime is 2 times u naught, and this is for order epsilon to the power 1 term, where u1 at 0 is 0 and u1 prime at 0 is 0, right? So this is what we are getting from here and here. Okay, so then when we can continue to solve this equation. We already know what is u naught. We can plug it on the right hand side. We see that u1 is tau cube by 12 times 4 minus tau, and we see that the two term expansion this time will be involving u naught and u1, the two term expansion. So u is u naught, which is tau by 2. So what have we got here? U naught is, so tau by 2 times 2 minus tau. So this is this u naught, and plus epsilon by 12 times tau cube 4 minus tau. So this is my second term. Okay, so then and so on for higher order terms. So now if we again, this is a problem we had initialized in one of our previous modules, where we had introduced the characteristic length scale and the time scale, and non-dimensionalized with respect to those scales, and arrived at this differential equation. And now we have solved this differential equation correct up to 2 order terms, order epsilon terms. So now let us go back and write down the dimensional version of the solution. So in dimensional variables, what we have is that x1, x is x of c times u, t is t of c times tau, where my xc was found to be, in the earlier module, was found to be v naught square by g. This is a problem from the projectile motion, and tc is v naught by g, right? And if we plug all these, we are going to get that from here we plug everything. So we are going to get the following form of the solution. My solution is x comes out to be t by 2 times 2 v naught minus gt plus g by 12 r t cube 4 v naught minus gt, right? And this is, notice that the first term is the linear term. It is the linear term, and this is the linear term. This is the first term, and this is accurate for small velocities, for small v naught, right? And if we have high velocities, we have to introduce higher order terms. This is accurate for, typically the first term is accurate up to Mach 2, although we are saying for small velocities, but still for projectile motion this is accurate up to twice the speed of sound. And this, if we introduce the second term, this is accurate up to Mach 10. So this is, whatever I am writing here is coming from directly from the observed experiments of projectile motions. Okay, so this is the non-linear correction. Non-linear correction. Okay. So that is what we have. Okay, so then let us now look at a system of differential equation and see how we can solve them. System of differential equation. So in the second example, we consider the system of equations. So ut is 1 minus u naught e to the power epsilon q minus 1, and qt is u naught e to the power epsilon q minus 1 minus q, and we have u naught equal to q naught equal to 0. And now if we using the same philosophy, that is we expand u and q using the power series, regular power series expansion, we see that u can be written as u naught plus epsilon u1. Each of these are functions of t, and we continue with higher order terms. Similarly, q can be written as q naught plus epsilon q1, and so on so forth. And we see that if we were to write epsilon, we try and write this factor, try to expand this factor epsilon q minus 1. This is going to be 1 plus epsilon q minus 1 plus epsilon square q minus 1 whole square. And well, what have we got here? We are writing the factor e to the power this, right? So this is the factor e to the power epsilon q minus 1 written in the regular Taylor series expansion. Okay, so now the factor which is sitting on the right hand side of the differential equation is exponential times u. So we have to multiply two power series expansions of u multiplied with the exponential to get the final power series on the right hand side of the differential equation, right? So what we see here is for the differential equation, we have that u naught prime plus epsilon u1 prime so on is on the right hand side we have, I needed to multiply this, so let me show this multiplication. U times e to the power epsilon q minus 1 after multiplication, so this is u naught plus epsilon u1 and so on so forth, multiplied with 1 plus epsilon q naught minus 1 plus and so on so forth. Then after this multiplication we get that this is u naught plus So u naught is the leading order term plus epsilon u naught q naught minus 1 plus u1, epsilon q naught minus 1 plus u1, and plus order epsilon terms which we leave, and so on. So now on the left hand side we get all these terms. On the right hand side is this following term, because the differential equation is 1 minus this. So we have to subtract the series from 1. So we have that the differential equations, the first one is left hand side is equal to 1 minus this factor here. So 1 minus u naught plus epsilon times u naught epsilon times u naught times q naught minus 1 plus u1 and so on so forth, right, plus minus order epsilon square terms and so on. And similarly q naught prime plus epsilon q1 prime and so on so forth, this is equal to, on the right hand side we have a factor which is u times exponential minus q. So we have that this is also equal to u naught, this is again the same series, u naught plus epsilon u naught times q naught minus 1 plus u1 minus, well, what have we got? Minus q1, minus q naught minus epsilon q1, that is q. So on the right hand side we also have a q sitting, so I have expanded q up to this order epsilon terms. So then we can start to solve. Again we have to, this is my differential equation. Similarly we can look at the initial condition. The initial condition is u0 is equal to q0 is equal to 0, which means all ui's u naught u1 u2 and all qi's q naught q1 q2 are 0 at t equal to 0. So then if we start to equate order epsilon to the power 0 term, we get that this is q naught prime is 1 minus u naught. So q naught, so u naught 0 is 0, and the order epsilon to the power 0 term for q is u naught minus q naught, where q naught of 0 is 0, right? And here we see that u naught is, we can start to solve these equations. So u naught is 1 minus et, and q naught comes out to be 1 minus 1 plus t times e to the power minus t. We have two first order equations, and we have solved these two equations to find the first order expression for the answer. Similarly, we can solve for order epsilon. We can do that. We will see that the equations, the differential equations are u1 prime equal to minus u1 minus u naught times q naught minus 1 and u1 at 0. So we have u1. So we have to continue to solve for order epsilon equation. We have u1 prime equal to the following, with u naught u1 at 0 equal to 0, and similarly for the q equation, q1 prime comes out to be minus q1 plus u1 plus u naught q naught minus 1, and q1 at 0 is 0. And now if we solve these two equations, we see we are going to get, we can keep plugging in the order epsilon to the power 0 solutions on the right hand side. So we see that u1 is half t square plus 2t minus 4 e to the power minus t plus 2 plus t e to the power minus 2t, and u2, well, similarly q1 is 1/6 of t cube minus 18t plus 30. I'm just writing the final solution here, times e to the power minus t minus 2t plus 5 e to the power minus 2t. So these are my two solutions, and with this u1, q1, u0 and q0, we will be able to write the two-term expanded form of the solutions for u and q. So the final form of the solution will be u of t is u0 plus epsilon u1. We can plug in the values of u0 and u1, which we just found use by solving the order epsilon 0 and epsilon to the power 1 solution. And similarly, q of t is q0 plus epsilon q1, right? And so on. Okay, so that is what we do when we try and use regular perturbation method in problems involving differential operator. Now we can also continue to generalize this power series expansion method in the regular perturbative expansion by using the generalized power series, where the powers are not the powers are not just positive integers, but they are rational numbers. So we are going to look at the more generalized version, scales and approximation. So not all asymptotic expansions are power series in epsilon, right? So not all asymptotic expansions are power series in epsilon. So we assume a general exponential form, right? So we have that f is f1 e to the epsilon to the power alpha plus f2 epsilon to the power beta plus f3 epsilon to the power gamma, and so on and so forth. So we are now going to use this well-ordered. So this is a well-ordered power series expansion. By well ordering, I mean that the powers alpha is less than beta is less than gamma, and so on and so forth. And these are all positive powers. So alpha is less than beta is less than gamma, and so on and so forth, positive powers. So which means that now we can use rather than these functions, we can use these scale functions. We can introduce the scale functions phi1 to be equal to epsilon to the power alpha, phi2 is epsilon to the power beta, and phi3 is epsilon to the power gamma, and so on and so forth. And notice that these phi i's for a regular Taylor series, the phi i's will be like follows. We have phi1 is 1, phi2 is epsilon, and phi3 is, well, phi1, phi2, phi3 is epsilon square. So this was coming from the regular power series. But for the generalized power series, the generalized Taylor's expansion or power series, we have that we have the following expansion that we have. Phi1 is epsilon to the power alpha, phi2 is epsilon to the power beta, and phi3 is gamma, where alpha, beta, gamma are in general not positive integers. Okay, so for example, I would like to again point out some quick example as to when these generalized power series will work. Notice that if we were to look at the expansion of e to the power negative 1 over epsilon, right? So we see if we were to use the regular power series or regular Taylor series expansion, this would have been equal to x naught plus epsilon x1 plus epsilon square x2, and so on and so forth, right? And we see that of course from here we see that x naught will be limit epsilon tending to 0 plus of e to the power minus 1 over epsilon. And if we take this limit, we will see that x naught comes out to be 0. Limit epsilon tending to 0 plus x naught comes out to be 0. Similarly, if we want to find x1 will be limit again epsilon tending to 0 plus we subtract x naught from the function e to the power minus 1 over epsilon. We subtract x naught and we divide by epsilon because that is what x1 is. And we see that again this is going to be 0. And so on, we will see that x2 is also 0. So which means that we are going to get that this is equal to 0, identically equal to 0 if we use the regular power series expansion of e to the power minus 1 over epsilon. So which means that something is wrong. The regular power series may not work, and that is because this particular function is transcendentally small. This is transcendentally small. This is transcendentally small with respect to regular power series, and that is why we are having a problem in representing this function using a regular power series expansion. So then well, of course, in this case we should have, to begin with, we should have used the generalized power series. Well, that can be readily shown that the generalized power series for this particular function will work, and that is not the goal of this particular discussion. The goal is that I wanted to show you that when can the regular power series fail. So the idea of using generalized power series for regular perturbation in differential equations follows the same trend that we have seen for algebraic equations. And I'm not going to show you more examples because the idea is almost identical to that of the algebraic equation. So next, in my next module, I'm going to introduce the second methodology, that is the method of singular perturbation. Namely, when is the method of singular perturbation important, and when does how does it work, and at what point we need to switch from regular to singular perturbation. So thank you so far for listening. Thanks a lot.